I want to do two different kinds of angular momentum collisions. And just throwing out a reminder, there's several pieces of this I need you to know. On Friday, some of the big takeaways started with reminding you that an object that's moving in a straight line has angular momentum, but we don't really talk about the angular momentum like that holistically. Meaning, if I have some object just flying through the air, or flying through space, saying that this object has a velocity in this direction, and saying that it has momentum is no big deal. We know that it has momentum because it's moving and because it has mass. Saying it has angular momentum doesn't make a lot of sense because of the way angular momentum is calculated. And although I've tried to bring this up a couple of times, I really want to kind of drive this home and be a little bit persistent. Angular momentum, lowercase l, for a point mass, technically is r cross p. But that's just it. R represents the point of rotation. The object's not rotating. But what R really represents, and this is what should be in your notes, this is the thing that you should really put down, with the highlighter. This is where you actually take the notes. R represents a point of reference. So it can actually be any point of reference. So I could say that this object has angular momentum relative to this point I've just drawn right there on the board. So in order to figure out what its angular momentum is, I have to draw a vector from that point to the object. And from that vantage point, I can calculate its angular momentum. But it's the angular momentum about this point. And it has to have all the same qualities that angular momentum has, which means it would have to have the same units, which is kilograms meters squared per second. It would have to have direction, which would be a rotational direction, because angular momentum has a rotational direction. It would have to be consistent. Now, the rotational direction is relative to the point in question. So if this is my point, the rotational direction would be whatever direction R sweeps out as the object moves. So for this example, the rotational direction would be into the board if I was using the right-hand rule, or clockwise. There's no reason to believe that this angular momentum has any meaning. I mean, it's having an angular momentum about some random point in space doesn't make a lot of sense and is not useful in the way that we would imagine having, a physics theory is useful in making predictions. The only thing useful about it is that I can say it has angular momentum about that point, which includes, of course, both the size of the angular momentum and a direction. But I could just as easily say that at the same moment, it has angular momentum about this point, suggesting that there's lots of different angular momentums for this object's motion. That's technically true, that I can pick any point in the universe and state that this object has angular momentum relative to that point. That's not the purpose. And it doesn't make a lot of sense to do that. Angular momentum, like any of the theories we've been learning, is supposed to have a useful purpose, and this one does as well. The angular momentum for this object's motion usually is considered relative to something else, some other object in which this object will interact. So we focus on the interaction between this object and the other object and use the other object, the thing it's going to bump into or collide with. We use the other object as the point of reference. So if you need me to direct you as to what to write in your notes, because some of you aren't, I would encourage you to write these words down. That we look for a common axis of rotation to be used when calculating angular momentum of a point particle. We look for a common axis of rotation. to be used when calculating the angular momentum for a point particle. Now, we didn't make it that far on Friday. Today, I want to use this kind of example because I want this example to be useful, and also because this example occurs a ton of times. You kind of saw one in the homework I gave you. It shows up a bunch. So we're going to have a standard collision between this bar and this object. We're going to say the bar has a rotational axis about its end. So something is holding it in position about its end. Imagine a meter stick that's been nailed into the wall so that it can rotate about the end of the meter stick. And this object is going to collide with the bottom of the meter stick. So, and I'm using the word meter stick, but I'm using it more anecdotally. I mean, I have some bar of length L and mass, we'll say capital M, and this object has mass lowercase m. It has an initial velocity lowercase v. Okay? The collision between the bar and this point mass is going to conserve angular momentum. It's important to understand that I have done something to this problem to change it from the example on Friday. The example on Friday, the only one we got through, was talking about that bar sitting on like a frictionless, surface, and it was not anchored to the surface, meaning it was able to rotate and move off after the collision. When I add an anchor here, I am adding an outside force to the system. That force is going to keep our object firmly in place so it can't leave the vicinity of this location. It can spin about this point, but it can't change location. We didn't finish.
Oh, but this is the same.
This is the same example I'm setting up, yes. But we didn't finish. We got right about to this moment when the bell rang. And I started to pick up the pace too quickly for some people to catch up. And I don't know if you realize, but so I have, we have options here about this collision. When I say options, remember, like any collision, the interaction here can be where the object strikes the rod and bounces off, strikes the rod and sticks to it, or strikes the rod and bounces backwards. There's lots of ways these two things can interact. And it doesn't really matter which choice we make. You have to be able to roll with what's going to happen in these problems. But just like conservation of momentum first semester, once we've identified that there's no external torque in the system, then we can state that the momentum just before the collision will have to be equal to the momentum just after the collision. I'm very careful to say the moment before and the moment after, because in this case, and the case for the problem I gave you guys for homework, gravity is acting in the system, which means the moment the object begins to swing upwards, momentum's no longer conserved. That's the hardest part about these, is trying to figure out when something is going to be conserved and when it's not. So I am trying to give you that piece of information you need right there, that we are looking at the instantaneous moment just before the collision and the instantaneous moment just after the collision. For this example, we're going to have our point mass stick to the rod during the collision, so that after the collision, there'll be the rod, and the point mass will act like a small dumbbell attached to the bottom of the rod. So it'll be a point mass at the bottom. This system is still fixed at this point, and there's likely to be an angular velocity after the collision. So I've established our before and our after case. Now, as we discussed Friday, the angular momentum can be calculated a number of ways. Right now, the rod has no angular momentum because it's not rotating, but the point mass does. And technically, it's R times P times the sine of the angle between R and P. And again, technically, r would be measured from the axis of rotation to where the object is. But as we discussed on Friday, we will probably use a different way of calculating the angular momentum because we don't know what r is. It's not given to us in most of these problems. In most of these problems, there's a collision that occurs, which means we advance the object to that instant just before the collision, the moment when they're in contact. And this is the moment that we consider the instantaneous portion of the collision just before contact. And the reason we do that is to give us a chance to calculate angular momentum based on r perpendicular. We know from our discussion on Friday that the angular momentum stays the same, that r is always getting smaller, but the angle is getting bigger. And they do so in equal measure so that we can calculate the angular momentum this way. This is how we will calculate the angular momentum almost 100% of the time. There are exceptions, but most of the time, this is how angular momentum is calculated. Right? So, for this example, our angular momentum, which is r perpendicular times p, is going to work out to be L, the length of the rod. That's what r perpendicular is in this instance. Because you consider that just before the collision, that's r, the distance from the pivot point to where the collision occurs. Times the momentum, which in this case is just going to be lowercase m times v. So this is the angular momentum just before the collision. Now, we're assuming that there's no external force in the system, but it's more than just an assumption. But we need to be careful. There actually, in this problem, is an external force in the system. It's right here. The pivot point causes a force on the object to keep the object from leaving this location. Because of that, linear momentum is not conserved. I'm going to say that again because I think more of you should make the pencils wiggle. There's an external force in the system because the object is staked down or is attached. That force acts here, right at the pivot point. It's to keep the object from leaving this location. Because of that, linear momentum is not conserved. However, and this is a big deal, this force can't cause a torque because it occurs at the pivot point. And a force at the pivot point can't rotate your object. It can't cause a torque. So although the net force is not zero, the net torque is zero. So force acts on the system, so momentum changes. But there's no torque, so angular momentum stays the same. Which means that I can set this equal to the angular momentum of the bar plus the point mass. Now,
is it 1/3 ml squared plus ml squared?
for the moment of inertia,
Yeah.
okay. As long as you were to say that, because I asked for the angular momentum, and you gave me the moment of inertia, I'm happy with that. So yeah, the bar has a moment of inertia of 1/3 capital M L squared. And the object acts as a point mass, so its moment of inertia would just be M L squared, because it is attached to the bottom of the rod. A lot of these problems do this so they can introduce a variable that's common throughout the problem. L is a common variable here. All of this, though, will be times omega, which is going to be the angular speed of the system after the collision. That's what makes it an angular momentum. So here we get LMV is equal to all of this stuff. This is very common. Very common. Now, the problem you guys had to work out for homework is really similar to this, except that during the collision, something else happens. So if we consider your homework question, and do me a favor, be looking at that homework question now, because I'm going to ask a couple of things about it. The homework question has the instant just after the collision highlighted in the problem, but not the instant just before the collision. Just after the collision, you've got this object kind of flying off in that direction, right? And is the assumption that the bar is fixed here and is traveling with some angular speed like that just after the collision? So this isn't about what happened just before the collision, but what happened just after the collision. Do you know what it must have looked like just before the collision? Savri, what do you think? What would it look like just before the collision? Yeah, I think that's what they're probably getting at. That's what they indicate in the question. So just before the collision, the bar was at rest and just hanging there. And the ball was approaching at a, I assume, horizontal velocity. So this is the condition just before the collision. Some V naught here. And the bar, of course, still fixed here at the top. Now, they go on to talk about something else that happens later in the problem, that the bar swings upwards until it is perfectly horizontal. It's important to note that this portion of the problem does not conserve momentum. The object stops. And the ball, I don't know where the ball is at this point. It's left. So going from, if I was to label these, this is A, B, C, 3 different points in this problem, you could not assume that momentum was conserved in going from B to C. There's an external force in the system that takes and stops the bar. And the ball isn't even part of the system anymore. But you can say that momentum is conserved from A to B. The problem is that after the collision, the ball is a separate object. It's got its own angular momentum still after the collision. Before the collision, we still have L, M, V naught for the angular momentum of the ball just before the collision. Now, I don't know what unit I'm supposed to use for the length of the bar. I'm just continuing to use what I was given in the prior example. But afterwards, the ball has some new velocity and travels off at an angle, and they want you to use this as your angle, correct? So we would have to assume that the bar has angular momentum on its own, just the bar, and the ball still has its own angular momentum relative to the pivot point. And there's a lot of little things here that I think students will make mistakes about. For example, the bar is pretty easy. It's still going to be I omega for the bar. But now we have to calculate the angular momentum of the ball after it recoils. And although we know what R is going to be, this length is still going to be R, I'll remind you that angular momentum is R cross P, which is R times P times the sine of the angle between them, which is not theta, by the way. The angle between them would be this angle, assuming R is measured right here. But I believe the angle we have to use in the problem is just a part of that. So when you're going to calculate stuff, you need to be very careful. This is going to be R times MV, probably times the sine of 90 plus theta. Because I know they asked for theta in the question. You've got to find a way to work it in. This is the angular momentum of the ball just after the collision. And all of this has to be equal to the angular momentum of the ball just before the collision. And you've got lots of issues because in this problem, my understanding is you don't know any of this. You don't know how fast the bar left after the collision. But I know some folks in my research class were talking about that. After the collision, it is perfectly acceptable to consider that the bar now has its own force acting on it from gravity, which means that the bar is going to be losing momentum. But gravity is just converting the kinetic energy into gravitational potential energy. So the bar's kinetic energy, its rotational kinetic energy, has to be equal to its gravitational potential energy when it comes to rest. The bar goes perfectly horizontal, which means the center of mass of the bar, which is right somewhere about there, is lifted from here up to there. So in this, the mgh is going to be mg times L over 2. Because the center of mass of the bar is lifted half of the bar's height. Yeah, and that has to equal 1/2 I omega squared. That's how you have to find the velocity.